So this is my lecture on networking. Networking is how computers are networked together, or how they talk together, how they exchange information. Each computer or electronic device that connects to a network will often connect into a jack, wall jack. Behind that jack are cables that often run to maybe underneath the desk or to some other central spot in a building where there's another jack, and then something called patch cables are used to connect from here to a switch or other networking device, and then out to cable DSL modem, other type of device that lets us get out to the internet. Beyond the home, a business has the same setup. Many computers hooked to some kind of firewall that then allows traffic to go out and wanted traffic to come back in, but the firewall also blocks undesirable traffic from getting into the network. And outside that network in the broader world, we have something called servers, web servers, video streaming servers, ad servers, bank servers. These are all computers, rack mount or case or looking like this, that provide data for the clients, home users, business users. These are called clients. Now, in a corporate business school network, beyond just what you have at your house, it's going to be a little bit more complicated, but follow the same basic principles that you have various clients or machines, printers, that connect to some sort of networking device, usually a switch. There's often multiple levels of switches. Switches connect to switches, and then those switches connect to devices that take us outside the building, through the firewall, into the internet. And each floor or building often has what we call a closet, a wiring closet, telecom room, where all the network cables run into. So if you look around, if you're in the lab, there's a number of network jacks along the walls. Some of those are actually not empty, they're wired. There's a cable going back for each of those jacks, going back to this closet and terminating in a patch panel up here, often in a rack. There's typically more cables than there are actually connections in the wiring closet. And as they need, they add something called a network switch, and they put a patch cable from the patch panel to the switch. And then there's usually a central connection, maybe sometimes multiple from a switch, that go out, often feeding into a larger data center, larger telecom room that has servers, networking hardware, and links to the outside world. Now, how computers in a network are connected together, that's a word called topology. And the physical topology is like a physical map of how the physical wires are run through the walls and which ceiling they go through, and it's very related to the actual physical environment. This is a physical topology. There's a logical topology, which is easier to draw, and network folks use that to understand how the various components in a network are connected together. And there's some principles with network topology that we just want to familiarize ourselves with. Now, perhaps one of the early, it's one of the early ones certainly. I mean, that's not necessarily simpler, but one of the earlier types of network topologies is called the bus network. And in this network, only one of these nodes, and each node is a computer, can transmit at a time. All these other computers can receive, but only one can transmit, because there's only one transmission medium here. Can't have two people talking at the same time. It's not very efficient because only one node can communicate at a time. But to get from here to here, it's what we call one hop. There's no intermediate delays, no latency is shorter. It's a fast connection. Now, on the other hand, if a wire breaks, if we break this wire, chances are the entire transmission medium goes down and the network's dead. Then the next step up, certainly, and this has been around a long time, but it's called the star network. In the star network, we have a central node or switch, and each node is connected via its own cable, its own wire, to that switch. If you accidentally cut a cable or step on it, you're only affecting transmission between that node and the central node. Some limitations are that you have limited connections here. In the bus network, you could keep adding machines, although certainly your performance overall would go down. In this one, the central node or switch usually has a limited number of connections, although in a common application, they just add another switch. Now, one also, I guess a good thing about this too is that this central node or switch can broadcast to each network. Sometimes you get network traffic that comes into here without a specific destination, and that network traffic asks the central node or switch to broadcast that information to all the nodes. Now, most home networks and business networks resemble this at some level. Now, there's a slight modification of the star network called the tree topology. And this is probably more like what PCC's network looks like. You have all these clients. These are generally the client nodes down here. And if this node wants to exchange information with this node, it's one hop up to this node, which simply switches it back down to here. Again, these nodes are probably computers, and in a real application, these nodes are not necessarily computers. They're specialized networking hardware or switches or routers. There's a little bit of latency or delay if node 4 wants to talk to node 7. It needs to transmit its information to 2. 2 needs to relay that to 1. 1 relays that to 3, and 3 relays that to 7. A little bit of delay. Transmission speed, which is at the speed of light, doesn't suffer. Just a little bit of delay in that each of these nodes has to receive something and then retransmit it. The good thing about this one also is that local traffic, so 4 and 6 can be talking, and 6 and 7 can be talking without slowing any of these other links down. If 4 wanted to talk to 6 and 5 wanted to talk to 7 all at the same time, they have to share bandwidth across these links here. Now, how does data get from one place to another on a network cable? Here's a network cable. The prevailing theory is that the cable is made up of tiny tubes, and in those tubes travel tiny mice. When you send data, it goes into the mouse's backpack. The mouse carries that across the tube, and at the other end types all that information into a tiny computer. It gets transmitted back out to the jack and then out to your computer. As much as we'd like that, how does it really work? Well, every device has a network interface card, or NIC, NIC. Now, it can be a discrete card. Often it's just a couple integrated circuits, or maybe just one integrated circuit on a motherboard. Sometimes it is a wireless interface, which is still integrated circuits. Still called a NIC, network interface card. Sometimes also, if you're looking at it from a software level, it is called an internet or a network adapter or Wi-Fi adapter. Adapter there still kind of having the same meaning as interface. Interface being interface from one way of talking to another style of transmission. All right. Every NIC has something called a MAC address. MAC stands for Media Access Control. If I'm looking at a network cable, the media is that network cable. It's the wire. That's the transmission medium. And the MAC or the NIC is the device that controls access to the wire. And each NIC device has a unique MAC address of this form. A lot of numbers and letters. It's a hex-based thing. So each position, this is a microcontroller that comes with a Ethernet connection, so it has a NIC or a network interface on it. This is the MAC address of this particular Arduino microcontroller, and each digit position can range from 0 to F or have 16 values. So it adds up to quite a few. Total combination or total number of combinations is pretty high. So each device that connects to a network will always have a MAC address, and in theory that MAC address is unique, although there are cases where you can clone MAC addresses, but normally they're unique. Now a network interface card puts out, and we're going to focus on Ethernet, puts out sometimes we call them frames and other people call them packets. An Ethernet frame to transmit data requires quite a bit of addressing and setup information. So a frame, there's some bits used to synchronize packets as it's going across the wire. A start a frame. You have to put the address, destination address in the frame. It's 48 bits. 48 bits for the source address, so there needs to be like a return address. You have some bits for length and type, and then there's the data and a packet. If you're streaming a movie, talking on the phone, using the internet for something, all that is broken down into packets, which with each packet having a maximum of 1,500 bytes, sometimes smaller. And then a frame check sequence just kind of at the end. This is for error correction. Once a device sends an Ethernet frame, it computes a frame check sequence. At the other end, the receiving device gets all this, computes a frame check sequence, and makes sure that the frame sequence the receiver computes matches the one that was transmitted. Now, if we go a little bit lower than this idea of Ethernet frames, fundamentally a network connection is really just a serial interface over a pair of wires. Now I know if you've looked a little bit ahead, a network cable has multiple pairs, but fundamentally it's one pair of wires, a receive and a transmit, and it's a serial interface. Normally Ethernet networking connections that we're dealing with today are full duplex, meaning that they can transmit and receive at the same time. There's a wire for transmit and a wire for receive. And ones and zeros are sent, so everything is taken from words into bytes into bits, and a bit, of course, is a 1 or a 0. Now, it's not really sending ones or 0, it's actually sending a voltage. It's not 5 volts and 0 volts, it's quite a bit less, and it's actually hard. You would be hard pressed to really see it clearly on a scope. It's pretty fast, and on the NIC there's actually fairly sophisticated physical devices that sense a voltage change on the wire and turn that back into a 1 or a 0 as the case may be. All right. Now, bandwidth across a pair of copper wires that are twisted to minimize interference. If we had two parallel wires, there'd be a lot of magnetic interference between them. When you twist them, it breaks up the magnetic fields. Anyway, the bandwidth for copper, twisted pair copper, maximum right now is about 10 gigabits per second, and it's not actually going to ever go higher than that for twisted pair copper. Fiber optic links have higher data rates, quite a bit higher, but fiber is more expensive to implement. So there's still a lot of twisted pair copper wires connecting our world. Now, when you have two NICs, or two network devices, establishing a link. So we take our computer and we plug it into the wall. It has to establish a link with the switch that's sitting in the wiring closet. So the NICs get connected with a cable. There's some circuitry in there that detects, there's something plugged in here, and link signals are sent back and forth. There's no data in this. There's no web page data. It's just a link. Well, actually, quite a few link signals. The NICs recognize that there's a legitimate Ethernet networking device plugged in on the other end of the cable. MAC addresses are exchanged. So each the client computer gets the MAC address of the switch, and the switch gets the MAC address of the client computer. The speed is negotiated. What happens is really fast packets are sent, training data is sent, and at the fastest speed. And if that's received correctly, then that's a speed. If data is not received correctly, if there's errors, it lowers basically the clock rate of the data going out. Anyway, once reliable data is going back and forth, the link is called up. Link lights are set, and the NIC will tell the computer that it's plugged into, tell the operating system software that it has a link, and here's some information about the link, here's the speed, and so forth. Now in your home network, everything downstream from the cable modem is Ethernet. We use that word Ethernet, but Ethernet tends to exist in a local area sense. Ethernet is not great for communicating over long distances. Now, your home network is networked in with the world, but using different technologies that are not technically Ethernet. Still has a high-speed serial interface. There's still packets and frames, but it's not the Ethernet that we're talking about. Anyway, home network is a star topology. For some people, these two devices are one device. Your cable company, Comcast cable, is connected into the same device that has all your Ethernet ports and your Wi-Fi antennas. Anyway, the switch has NICs. Now it's probably one chip or a couple chips, but it's still a network interface device. And this switch that all your devices are connected to will keep track of all the connected devices. So if this multimedia center wants to send something to the PC, or the PC is asking for stuff from the media center, the switch will know where to send it. It knows which port this media center is plugged into. So it has a table of MAC addresses. Now, let's talk about wired Ethernet first. And the most common networking standard in homes and businesses is wired Ethernet. Speeds range from as slow as 10 megabits per second, in theory up to 10 gigabits per second. And we're still, again, talking about twisted pair wires. You can get faster data over fiber optics. Most common speeds you'll find in a home or a business is 100 megabits per second or 1 gigabits per second. New construction is certainly wired with cabling capable of 10 gigabits per second, but not all hardware actually supports that speed. It's a star configuration where each wire has only one NIC at each end, so it's a point-to-point connection setup, not a bus topology. There was an older Ethernet over coax topology. I don't think you'd find it except anywhere, maybe an older factory setup or something. The cables are shielded. People don't like to change. You might find that. In that, you had a coax cable, single coax cable running, snaking its way through all the connections. Anytime you need to make a new connection, you cut the cable, put in a T, connected it to the device. Now, network cabling, the wires that we use for Ethernet, are manufactured to very strict standards, and those standards have are called CAT standards, CAT. So we call the different wires CAT 1 through CAT 6. CAT 1, that's just a simple phone wire. It's not capable of high-speed data transmission. You probably can't buy CAT 3 anymore. You might see it in some older setups. What's more common is CAT 5 for 100 megabits per second, CAT 5e for 1 gigabits per second, and for new installs, something called CAT 6, which is rated to 10 gigabits per second. Now, this wire is unshielded. Sometimes you might see in noisy industrial areas there will be a shield on the wire, and RJ45 is the name of the jack. It's the connector. And the cable assembly, 4 pairs of wires per cable. The wires and connectors are color coded, and the connector box, if you buy a box of connectors, always comes with whenever you buy something connected with wires, it usually comes with a color code chart, or you just look it up on the internet. Now here's a little diagram, a little illustration of the different cables. CAT 3 is thinner, only has 2 twisted pairs. CAT 5 and CAT 5e, 4 pairs of wires, and each pair will follow green with white stripe, orange with white stripe, blue with white stripe, and then brown with white stripe. I know that looks like a white arrow, but it's really, or white wire, but it's really brown with a white stripe. The difference between CAT 5 and 5e, they basically got much more strict about how the wire. There's a very strict spec that talks about how many twists the wire should have, the wire gauge, how the pairs are twisted together in the cable. And then we move up to CAT 6, where same 4 pairs of wires, same color coding scheme. This one I don't think is meant to imply that it's shielded. If there was a shield, there'd just be a aluminum foil shield around this wire. What's different about CAT 6, though, is there's this center plastic, usually some kind of plastic piece of stuff. The wire pairs twist around that, and it serves the function of keeping the wire pairs just a little bit further away from each other, and basically making it so that we can run it at a higher rate without, again, having that magnetic field business that when you push currents through wires or have changing currents through wires, have that magnetic field interrupt other wires. Anyway, CAT 6 is actually, from the outside, this looks deceptive. The thickness of the wire is the same. You have to look on the wire, say CAT 5 or CAT 6 on the wire, or when you cut it open, you'll see this plastic conductor business in there. And here's another picture that shows, again, that plastic star cross thingy just keeps the wires aligned in a certain way. And of course, these are also, it doesn't show, this is one cross section. These wires are twisting, there's a spiral inside the cable for the wires as well. But in the CAT 5, they don't have that quite as much control over the spiraling. Each pair is spiraled, but CAT 6 anyway is just faster. One more little diagram showing some characteristics. Frequency, CAT 6 runs faster, again, because of that stricter spiraling and wire control inside the cable. 250 megahertz. Has a little bit of impedance. This doesn't show the resistance. There is a resistance in the wire, a couple ohms per 100 feet or something. It's a little bit more expensive. We'll talk about this later, but Ethernet, of course, there's no physical limit to the cable, but from an electrical point of view, the longest you can have a cable run is about 300 feet or 100 meters. Now, you can have Ethernet connections that go a lot farther than that, but that's only because there are intermediate switches or intermediate networking devices that separate those 100 meter spans. Data performance, again, 100 gigabits per second, usual, possibly up to 10. Now, within that network cable, the wires eventually make their way out to something called an RJ45 plug that has to be wired in a very specific way. Now, there's two standards for how the wires map to the pins of the plug, T568A and B. The one that's probably more common these days is the T568B, and the only difference is I think the orange wires are swapped. And actually, it doesn't make any difference which standard you use as long as both ends of the cable follow that standard. And from left to right, looking at the I guess the bottom, I consider this the bottom, although the clip of the plug is pointing away from you. You know, it's orange stripe orange, then the green stripe, solid blue, blue stripe, solid green, and then brown stripe, and then brown wire. In the lab, you're going to make one. We have the tools, we have the wire, you have the plugs. I'd suggest looking at almost any one of these YouTube videos on RJ45 network patch cables. I just search for RJ45. Watch a video the first time. Almost any of these are fine, and we'll talk about it in the lab as well. Let's get back to a quick discussion of fiber optic networking. So fiber is using light instead of copper wires, light across a fiber tube or fiber wire. You get more bandwidth. The lights and electrons move at the same speed, but fiber has immunity to noise, magnetic effects. Twisted pair has that limit of 100 meters per nix before the resistance in the wire gets too big. And you can run it at 100 or 100 meters or further, but it will go slower and slower, so slow as to become unusable. The 100 meter limit is for the standard speeds. All right, signals on fiber can go 2,000 meters, and they pack more data on a fiber because most fiber is something called multi-mode fiber, where you have light at different frequencies, each of which is considered like a data stream that's carrying its own information, but all that light at different frequencies can go on that same cable. And here's a quick picture of multi-mode fiber. Single mode, you have one light frequency going at this speed. Multi-mode means different wave or different light beams are traveling in the same fiber. Again, more data, much more higher bandwidth. Fiber can carry a lot more data than a copper wire.